Our planet is one of billions, or, to quote Carl Sagan, billions and billions of fairly similar worlds. In spite of this, ours is the only one as of yet known to us to support life. Why exactly this may be is a question that has intrigued and stumped people for hundreds of years. And as time goes on and our technology gets better and better, this seemingly becomes increasingly unlikely. We can detect more in space than ever before. We have sent forth radio signals in the hopes of receiving a response, and we have simply had more time to encounter other life. And yet, nothing. This begs an important question, though it may not be an obvious one at first, and it is all based around a key assumption that has everything to do with man's current struggle against the climate crisis, a battle which may be our last. How long do species that develop intelligence and become technologically advanced survive for? For all of this and more, let's look at the Drake equation.
This is one of the great questions. How many advanced civilizations capable, at least of radio astronomy, are there in the Milky Way galaxy?
This is from Carl Sagan's Cosmos miniseries, based on his 1980 book of the same name. This section is an excellent breakdown and sample calculation of the Drake equation. To put it simply, this equation provides n, the number of technologically advanced civilizations in the Milky Way galaxy, by multiplying the following factors together, straight across. N star, the number of stars in the galaxy, times Fp, the fraction of those stars with planetary systems, times Ne, the number of planets per solar system with an environment suitable for life, times Fl, the fraction of suitable planets on which life actually emerges, times Fi, the fraction of life-bearing planets on which intelligence develops, times Fc, the fraction of civilizations that develop a technology that releases detectable signs of their existence, i.e. radio astronomy, into space. And finally, and crucially, F big L, the fraction of a planet's lifetime that is graced by a technical civilization's presence. While this equation may seem difficult at first, it's really quite simple. However, it is based on some decent unknowns and critical assumptions. In fact, in 1961, when astrophysicist Frank Drake developed this equation, there were even more unknowns and assumptions feeding into this than there are now. But by building upon some of the work that's been done over the past 75 years, we can today provide a far better estimate for some of these values. In 2016, Adam Frank and Woodruff Sullivan released a paper which simplifies and updates the Drake equation. One of the things they pointed out is that NASA's Kepler satellite and other scientific endeavors have given the approximation that roughly 1/5 of stars have planets in habitable zones, defined as regions where temperatures can support life as we currently know it. If forms of extraterrestrial life can survive outside of this value would, of course, be higher. But for now, this is what we know. This equation logically steps down in scale and forms a basic sentence. Simply put, we are looking at how many stars there are, how many of these have planets suitable for life, and on how many of these planets does intelligent life actually arise with technologies that release detectable signals of their existence into space. Alright, so now let's take a stab at actually calculating this. So we're going to begin with n star, which if you remember is the number of stars in the galaxy. Inside the Milky Way galaxy, we know there is at least 100 billion stars. There are probably more, there could be more, but we're going to go with this for now. So n star is 100 billion. That is a lot. Times F of P. F of P is the fraction of stars which have planetary systems inside of habitable zones. For this one, as we mentioned earlier, we know that this figure is 1/5 based upon Kepler satellite data and other scientific endeavors that have taken place over the past 75 years. This is about 1/5. Multiply this by Ne. This is the number of the planets in these systems that are actually inside of habitable zones. For this one, we're going to go with about 2. This is a pretty decent figure. If you look at our solar system as an example, we actually have more planets that could inhabit life based upon the temperature ranges that we are aware of. This includes Mars, Earth, obviously, Jupiter, some of Jupiter's moons. So given this, 2 is actually a fairly legitimate and reasonable estimate. Multiply this by FL, the fraction of planets on which life actually develops. This one is a tricky question, and people put this in many different places. For myself, we are going to put this at a quarter, 1/4. Carl Sagan actually put this at a half, but I believe that 1/4 is a more reasonable estimate. You have all the building blocks for life, yes, but will it actually happen? It's another question entirely of more sophisticated life, but life itself, perhaps not the most rare or complex thing to develop. Life on Earth developed fairly quickly after the planet was created. So we're gonna go with a quarter. I mean, let's take a step back here actually for a second and calculate as we go. So 100 billion by a fifth, that's 20 billion. Multiply that by 2, 40 billion. By a quarter, obviously you're looking at 10 billion up to this point. F sub I is the fraction of these worlds on which intelligent life develops. Now for this one, we're actually getting a significantly wider range of answers among the scientific community and people that believe different things about this. For some people, there's the idea that life develops and it almost necessitates that it tracks towards intelligence and complexity. Other people think that developing to a point where there's complex thought, intelligence, etc. is actually exceedingly rare. So for this, we're going to try and find a good middle ground figure, and we're going to go with 1/10. Out of all planets that develop life, perhaps only 10% develop intelligence. Now, for our last figure here, F sub C, this is the fraction on which complex technological civilizations evolve. Similarly, there are those that believe that intelligence would necessarily track towards complex technological advancements such as radio astronomy. However, is that true? Perhaps intelligence does not necessarily result in complex technologies outright. For this, we're also going to derate it from the same amount, 1/10. And part of the reason for this, 1/10 by 1/10 is 100th, aka 1%. It's fairly safe to say, and it's a decent estimate to say that all life that develops, perhaps only 1% of that would develop into an advanced technological civilization. So we're going to multiply 10 billion by 1/100th, and this is going to give us 100 million. Bang! There's our answer, right? We're done? Not quite. We have one more input, F big L, and this is where things get really interesting. If we look at ourselves as our only example, the Earth has been around for 4.54 billion years. We have had intelligent life that is releasing detectable signals of its existence into space for only about 80 years, which is an unfathomably small percentage, near zero. We can approximate it as 1/100 million. With this as our F big L value, N, or the answer to the equation, the number of technologically advanced civilizations in our Milky Way galaxy would be about 1. But we're still here. We're still here, and we hope to be for many, many years to come. But will we? Looking into the future at the timescale of our planet, what percentage of Earth's lifetime will humans occupy? Will we figure things out, begin to change our ways, and change course before it's too late? We know the science. We know what we are doing to ourselves and to our planet. Without immediate action, our future does not look promising. We could irreversibly terraform our planet such that it is no longer suitable to support us and self-implode in as little as a couple hundred years. But if we do figure it out, if we do make a change, we could last for tens or hundreds of thousands of years, or possibly even millions. If we make it, if intelligent life can last on a planetary timescale, FL could go from this to this. Instead of having one intelligent civilization, the number of civilizations in the galaxy could instead be measured in the millions.
Millions of technical civilizations.
Is the reason we have not found any evidence of life in the universe because intelligent life necessarily tracks towards self-implosion? Is it possible to survive under the weight of our own advancements? Our newfound capacity for great destruction? Decisions we make with implications far greater than we realize until it is too late? The choice, at this point, is entirely with us. Only we can write our story in the great cosmic narrative. As the only intelligent civilization known to us, our decisions define life in the galaxy as we know it. If we can make it past this great bottleneck, we can prove something far greater than ourselves. Life is not some fleeting mistake. Life is something that can evolve, is meant to evolve, and has a place in the universe. It can survive and thrive on planetary timescales. It can respect its home world and its neighbors as much as itself. And if not, then it will perish. The choice is ours. I really hope you enjoyed watching. Thank you very much. If you want to learn more, understand more, and talk more about climate science, climate change, atmospheric science, environmental science, these are the types of things that I cover on this channel. Would love it if you would stick around. I also engage in some cleanups, and we're going to have our first big cleanup video at 100 subscribers, and then it's milestones from there going on into the future. So if you want to be around for that, please subscribe, stick around, like the video if you did, comment, etc. I appreciate your attention and your time, and I will see you next time.